So in the last lectures we have introduced the Chern class and the Pfaffian classes of complex or real bundles respectively, and we have looked at various differential or characteristic classes which are derived from it using additive and multiplicative sequences. And today we will introduce the third main characteristic class, namely the Euler class for real bundles, oriented real bundles. And this is important. This occurs in the Chern-Gauss-Bonnet theorem, which I will state later. And but first we have to do some linear algebra to introduce the invariant polynomial on which this class is based. And this thing is called the Pfaffian. I'm going to discuss it in detail since it's typically not treated in the linear algebra courses. All right, so let's do the following thing. So I will use this notation Sn for this for the permutation group on n letters. So that's the set of all group of all permutations of set 1 up to n. And recall that the determinant can be written down using these permutations. So recall that for an n by n matrix, I'm doing it only for real coefficients for today, that's good enough for us, that for the determinant of A can be written down by summing over all permutations, sigma, then there's the sign of sigma of the permutation, that's plus or minus 1. And then we take the entries of the matrix, A1, sigma 1, all the way up to A(n), sigma n. So that's the usual definition for the determinant. It's not practical for actual computation, but it's an easy way to define it. And the aim of the Pfaffian is to define another. So you see, this is a polynomial in the entries of the matrix, and we have used it when we defined the Chern class. And now we want to look for a different invariant polynomial, and that is going to be a polynomial which squares to the determinant for special matrices A, namely for matrices which are skew-symmetric. And that's the aim, and that is going to be the Pfaffian. So if A is a skew-symmetric matrix, and remember the skew-symmetric matrices are actually the condition of being skew-symmetric. This is coming from a Lie algebra, namely these are the matrices in the Lie algebra of the orthogonal matrices. So if we have a skew-symmetric matrix, so that's a German little o, so that means, what this exactly means that A transpose is the negative of A. Then for the determinant, we have the following observation. So the determinant of A is then, as usual, as always, the same thing as the determinant of the transpose, but now the transpose is the negative of A, and we can pull out this minus 1 sign from the determinant, and this comes with the size of the matrix, so this comes with a minus 1 to the n times the determinant of A. And so if we compare the left-hand side and the right-hand side, and then we see that if n is odd, this implies that the determinant is 0, right? So hence for n odd, the determinant of A is 0. And that's the reason why we will basically only look at even dimensions. Because for skew-symmetric matrices for odd n, it's easy to define the square root of the determinant will be 0. So the interesting case is the even dimensional case. Okay, good. And let me also remind you of another thing about skew-symmetric matrices. which I always treat in the linear algebra course, namely that's the normal form of skew-symmetric matrices. So the normal form of matrices A, which is skew-symmetric. And now I restrict already to the even-dimensional case. It's as follows: there exists an orthogonal matrix B such that if I conjugate A with B, so looking at B A B to the minus 1, then I can bring it in a form, in a very nice form. Namely, it consists, it's a block diagonal matrix, and there are 2 by 2 blocks on the diagonal. And the skew-symmetric 2 by 2 block is very simple. There's zeros on the diagonal, and looks like this. So I can bring it in this form for some real values, mu1 up to mu n. Okay, so that is the normal form. In particular, then if you look at the determinant of that thing, so the determinant of A, which is the same thing as the determinant, so determinant is invariant, right? So it's the same thing as the determinant of that thing, and the determinant of this we can directly read off. It's just the product of the determinant of these blocks. And each block has determinant 0 minus mu1 squared, so we get mu1 squared all the way up to mu n squared. So we see already there's the determinant of a skew-symmetric matrix naturally appears as a square. We want to define a new polynomial, which for this kind of matrices will give us the value mu1 up to mu n without the squares. That will be the Pfaffian. Okay, so let me write it down. Definition. The Pfaffian of a skew-symmetric matrix is defined by Pfaffian of A. So as I said, the odd dimensional case is trivial because the determinant gives 0, so in this case we just define it to be 0. This is 0 if n is odd. The interesting case is the even dimensional case. So if n is of the form 2n, and I give you the formula. And the formula is first a scaling factor, which we will understand later, 2 to the n times n factorial. And then there's a sum over all permutations. But unlike for the determinant, we are not taking permutations on n letters, where n is the size of the matrix. Rather, we take only half the size of the matrix, so we take permutations in only n letters. And then we write down the signature of that permutation times. And now we have a sigma 1, sigma 2, all the way up to a sigma 2, n minus 1, sigma 2n. So for the determinant, each permutation appears only once at each entry, whereas here the permutations appear in both indices of the entries. That's why we only have permutations on m letters here. So that is n minus 1 all the way up to n. so we see directly from the definition that Pfaffian, so this is a homogeneous polynomial in the entries of the matrix, and the degree of degree is so that is an M. That is an M. Okay, so let's see. Well, let me first get the M's and N's right here. So that's an M. That is an N by N matrix. So like that. So now it should be correct. So it's a polynomial of degree M, homogeneous polynomial of degree M on this V algebra O N, so which is 2n. To make it like this. So examples. So the simplest case certainly occurs when M is equal 1, so we have 2 by 2 matrices. And now a general skew-symmetric 2 by 2 matrix looks like this, of course. I'll come back to this example in a moment. So let me first rewrite the definition of the Pfaffian so that we have less terms. So that's the following definition. So we can restrict the sum to special permutations. And this will explain also this prefactor here. And these are the so-called partitions. So sigma in Sn is called a partition this is 2n to make the point that this is even. It's called a partition if it satisfies the following things. So we have we look at its pairs, the first two, the second two, etc. And I always assume that the pair is ordered in the following way. So that I have sigma of 2i minus 1, the odd case, so that's always less than sigma of 2i. So that's one condition, and so we look at these. So we have a permutation, and then we look at pairs, the first two, the second two, etc. So each pair is ordered, and now we order the pairs, and we order them by the first entry. So we have that sigma 1 is less than sigma 3, is less than sigma 5, etc. So that's just a condition on a permutation, and if they satisfy, I call it partition. And the set of all partitions is denoted as pi n. It's pi n. It's the set of all partitions sigma in S. Okay. Yes, I'll give examples in a moment. And when we do the computation of the partition for simple cases, so okay, that's a good example now. So if m is equal 1, of course there's only 1, right? Then we have just one pair. In this case, I1 consists of only one partition, and I use this notation for permutations, which gives us the values of the numbers in the second row. And it's the identity here. There's only one further permutation in this case where these two are flipped, but that would violate this condition. And for m equals 2, that's what we wanted to see. There are 3 partitions. So there's the identity, of course, that's always there. And then then these conditions are obviously satisfied. But what else can we do? Well, we also have, we can take the pair 1, 3 here. That's the first pair, and then the other pair is 2, 4, and we have to just, so this has to be less than that, this has to be less than that, and this has to be less than that. And there's a third one, 1, 2, 3, 4, which would be, you will always start with 1 here. Then instead of 3, we can take 4 here. Then we have 1, 4, and the other pair is then 2, 3, and it has to be this pair. So these are the 3 partitions in this case. All right, and yeah, okay. And now, why? My point is now, each permutation can be converted into a partition with 2 operations. And these 2 operations basically do not affect the term that we have here. So let's see. I can convert any permutation into a unique partition as follows. So let me write this down. 1, 2, all the way up to 2n minus 1 to m. And let me call the value sigma of 1 I1, and the value of 2 J1. And then the value of 3 would be I2, and then 4 would be J2, etc. So we end up all the way to IM and JM here. Just a notation. So to reflect the distinguished roles of these. So in this notation, this condition would mean that IK is always less than IJK. And this condition would mean that I1 is less than I2 is less than I3, etc. And yes. So convert it into a partition. How? First, what you do for each pair, you interchange the 2 values in case they violate this condition, right? So if I1 is larger than J1, then I interchange them. If not, then I leave them as they are. So interchange IK and JK if necessary, such that IK becomes less than JK. That's one thing you can do. And then all the pairs are in the right order, so these conditions are all satisfied. And then I in addition have to satisfy these conditions, and for this I have to reorder the pairs. So that's the second step, interchange pairs IK, JK, and let's say IL, JL if necessary. Such that the second condition holds. Such that I1 becomes less than I2 becomes less than 1 to IN. Yeah. All right. So these are the 2 operations. First, bring each pair in order, and then bring the pairs in order. And this then will result in a permutation. And now let's see what happens if we do this. What happens to the terms that we are summing here? If we interchange 2 things in a pair, then the corresponding permutation is altered by a transposition. And this introduces a minus sign in the signature, in the sign of the permutation. So if we perform a step 1, then this sign of the permutation changes. But then we also interchange the indices in one of these factors. And now here we use that the matrix is skew-symmetric. So this interchanging the indices in one factor also introduces a sign. So that the whole expression is not changed. And if we perform one of the step of the form 2, then we interchange two pairs. If we do that to a permutation, nothing changes. This is an even number of transpositions. And here, for these terms, it just means that the factors are, the order of the factors is changed. So nothing changes either. So also for the step 2, nothing changes here. So therefore, any partition that is transformed in this manner to a permutation for the corresponding term in the sum can be replaced by the term for this partition. And now let's see how many permutations get converted into the same partition. So let's count that. But first now, operations 1 and 2 do not change the sum here. So that's what I just explained. And now let's see how many different permutations get converted into the same permutation, in the same partition. Well, let's start with the partition. Let's undo the thing. So if we start with a partition, then we first can reorder the pairs in an arbitrary manner. So we apply a partition on the set of pairs. How many are there? Well, the set of partitions always on k letters has k factorial elements, and we have m pairs here. So we get m factorial many possibilities to reorder the pairs. The number of permutations which get converted to the same partition is m factorial. But then, in addition, we can also undo step number 1. So we have the choice to reorder each pair. And we have m pairs, so we can choose arbitrarily many out of these m pairs. And this is how many possibilities? If I can freely choose to reorder or not reorder any of the m pairs, how many possibilities do I have? Well, if it was just one pair, how many different possibilities would that be? 2. I could do it or could not do it. Now if I have 2 pairs, how many possibilities is it? I can do it with pair number 1 or not, and I can do it with pair number 2 or not. So it's 2 times 2. And if I have m pairs, I can do it with any one or not do it. So it's 2 to the m possibilities. That's what we get. If you look at the definition here, you see the answer already, right? So this is exactly the term that I have to divide it out. So to conclude from this, we can rewrite the Pfaffian in the even case by only summing not over all permutations, but only over the partitions Pfaffian. And then this term goes away, and the solvent is unchanged. And that's of course better for computation because I have less terms here. A lot less terms actually. And okay, so let's now look at examples, and we have the partitions listed up here already. So if m is equal to 1, there's only one partition. So for the m equal 1, so these are 2 by 2 matrices. And as I said, so these have, of course, the following form. Now, what does this condition give us? There's only one partition. We have to see this on the upper board, namely identity. And this has signature 1 plus 1. And I have to just, so the signature is 0, the sum is consists only one term. And I have to just take one term here. Sigma of 1 is 1, sigma of 2 is 2. So I have to take the 1, 2 entry, first row, second column, which is mu. So that's what we have to discuss. And for m equal 2, so these are 4 by 4 matrices. So let's see how a general skew-symmetric matrix looks now. So we have A, B, C, D, E, F. These are arbitrary, and then it's skew-symmetric. So it's minus A here, minus B, minus C. And then we have minus D, minus E, and minus F. And that's the general skew-symmetric matrix 4 by 4. And now we have 3 terms in this sum, as we see. And let's see. So the first term corresponds to the identity permutation. That has signature plus 1, of course. And then what we have to take, just the identity here. So we get the entry 1, 2, which is A, times the entry 3, 4. Entry 3, 4 is F. Now the second permutation that occurs is a transposition in these two terms. So it has negative signature, so we get a minus sign. And then we have to take entry 1, 3, 1, 3 is B, times entry 2, 4, 2, 4 is E. And then the last partition. So this one has, so let's see, in order to get this to the identity, we have to flip 4 twice. So this gives us signature plus 1, so plus 1 sign again. Then we have to take entry 1, 4, which is C, times entry 2, 3, which is D. So that's the Pfaffian in this case. All right, and now you see the pattern. Let's also look at a second example, namely this, because we will need it later. Namely one which looks like this. If we take the Pfaffian of a block matrix, where we have zeros here, and the identity, or let's say minus the identity here, and plus the identity here. That's also skew-symmetric, obviously. So what would the Pfaffian be? Well, how many partitions contribute? So see, in this definition here, if we use this formula for the partitions, then the last term, so yeah. So we have to look to check which pairs actually do give us non-zero contributions, right? And most of the entries in this matrix are 0, so there's not many options. And well, which pairs do give us that and ordered in the right way? Well, if you look at the first row, then there's only one non-zero term, namely the one corresponding to the first row and the m plus first column. Then we go to the second row, and then there's only one term possible, namely the m plus second column, and so on. So that means the only partition, the only option to get something non-zero here would be the following partition. So in the first row, I have to take the n plus first column. No other option. In the second, I have to take the m plus second column. No other option for the second row. All right, so this goes all the way up to, and then first do it all the way up to m minus 1 and m. So this is nth row here. So for the nth row, we have to take the 2mth column. No other option for that. And then we proceed, then we have m plus 2, m plus 3, and here we get the m plus first, sorry. So this is, so the last pair which we have is m and 2n. Right? So this goes all the way up to 2n minus 1 to 2n. So this way. I mean, there are more permutations, because all the permutations that you get through operations 1 and 2 will give us the same sum. But if you insist on being the partition, that's the only possibility. Only this partition contributes. Okay. Now, in order to determine, so that's only one summand here. So we need to know the sign of this permutation and these entries. But these entries that we have here are all minus 1. So these entries here give us n factors of minus 1. And then we have to look at the signature of this permutation. So what's the signature of this permutation? So we have to check how many transpositions we need in order to convert this into the identity permutation. So what would we have to do? Well, we can push the 2 in front, one transposition. Then we push the 3 in front, then we have 2. And so on. So 2 needs 1, 3 needs 2, 4 needs 3, etc. And the last one needs m minus 1. So we have 1 plus 2 and so on all the way up to m minus 1. This is the number of permutations, transpositions that we need in order to arrange this into the identity permutation. Okay? Question? Yes, indeed. Thank you. It's always the end. Okay, so and this is minus 1 to the m times minus 1, and this is m times m minus 1. All right, so that's the result of the Pfaffian for this one. We will need this later. Good. Now the first important lemma for these Pfaffians. if we want to use the Pfaffian data as for the definition of characteristic classes, then it has to be an invariant polynomial, right? And so we have to see what the invariance properties are of this Pfaffian. So here's the answer, lemma. So prepare first. The invariance properties I'm getting ahead of myself. So first let's see what we have. We would like to treat these block matrices which I've just erased coming from the normal form. And for that it would be good to know what the answer for that is. So for a skew-symmetric matrix of size, let's say 2 and 1, and B a skew-symmetric matrix of size 2 and 2. So then we get again a skew-symmetric matrix of size 2 and 1 plus m2, and we have this formula here, so it's just this, like the corresponding formula for determinants. And proof also more or less directly follows from the definition, namely, let's look at this matrix. Now, when we apply this definition using partitions, then which of the partitions, again we have lots of zeros in here, so not all partitions contribute, and only such partitions contribute which contains pairs completely in the set for M1 and also completely in the set for M2. Anything else will hit a zero and will not contribute. So we can write this formula for the Pfaffian for this type of matrix by saying that we sum over all partitions on M1 and partitions on M2 and combine them to a partition for M1 plus M2 by first looking at the pairs coming from this partition and then looking at the pairs coming from the second partition. So this will give us, then this will give us first entries here coming from the first partition all the way up to this one. And then we get the pairs coming from the second part, so which will be sigma 2, 1, sigma 2, 2, all the way up to sigma 2, 2 and 2 minus 1, sigma 2, 2 and 2. And what about the signature of the corresponding partition? Well, in order to check the signature, well, if you have two partitions and you put them behind each other and you want to check how many transpositions you need to get in order to get all the way up, then it's just the one number plus the other number, so we get the signature, the sign of the first times the sign of the second partition. I'm not sure if I make myself very clear. So I'm summing over, not over all partitions, but only over those partitions that contains only pairs in the range from M1 and in the range from M1 plus 1 to M1 plus M2, because otherwise you would hit an off term here, which is 0. And this is why I'm summing over these things, and not over all partitions on M1 plus M2. That's the reason. And then this is the corresponding term that I get from the general formula for the entries. And then I have to check if I put together two such partitions to one partition and the whole set from 0 all the way to M2 plus M1, then how do the signs relate, and they relate like this. Yeah, simple. Maybe I just leave this as a simple combinatorial exercise. And now we see that we could take the sum apart by first only summing over sigma 1 these terms and those terms times the sum over these terms, taking this times that. So then this gives me directly the formula for the Pfaffian of A times the Pfaffian. In principle, it's the same argument as if you want to prove it directly from the definition. All right. So that's an observation. And this is useful, for example, we have seen that the normal form gives us a sort of block form for our matrices. So if we want to compute the Pfaffian of a skew-symmetric matrix in normal form, then we just have to take the product of the Pfaffians of the blocks by this lemma. And this we have computed earlier. This gives me mu1 and this gives me mu(n). And remember the determinant of this matrix is mu1 squared all the way up to mu(m) squared. So that's already good. So this thing squares to the determinant. That's good. All right, and now we can discuss the invariance properties of the Pfaffian. And the crucial statement is this proposition: let A be a skew-symmetric matrix and B any matrix of the same size. Then, if I look at the matrix BAB transpose, and this is again a skew-symmetric matrix, why? There are two possible answers here. Yeah, that's correct. Yeah, you just transpose the thing. This gives you BA transpose B transpose, because the orders have to be reversed. And then the fact that A is skew-symmetric implies that the whole thing is skew-symmetric. There's also a different answer, namely, at least if B is invertible, namely, skew-symmetric matrices are also representing skew-symmetric bilinear forms. And this thing here is just giving you the formula for the base change. But whether or not a symmetric bilinear form is whether or not a bilinear form is skew-symmetric is not dependent on choice of basis. So that's why we must have that invariance. Yes. Okay, so now I'm claiming that the Pfaffian of this is related to the Pfaffian of A by multiplying the determinant of B. So that's the invariance of it. Okay, so let's see why that is true. So PF sometimes stands for proof and sometimes for Pfaffian. So by capitalized it stands for proof and small letters it stands for Pfaffian. The Pfaffian, so left-hand side of this expression. So let's really write it down using this definition with partitions. So then we get, oh no, I'm using the original definition with permutations. So I have this factor to carry along. Then I have permutations. Then I have sign of the permutation. And now I have to take this matrix here, this product of three matrices, this matrix, and apply like this, and then take a look at particular indices here given by this permutation. So the first, the left index is given by sigma 1 times something, and then here we have the last term, but there's a transposition here, so the things get interchanged. So it's again the first one, which is sigma 2 times something, and not dot times sigma 2. All right, but in fact, here we have matrix multiplication, which we can also spell out. So this would give me a K1 here, and an L1 here. And then in addition, we have to sum over K1 and L1, of course. So let me add this here. Sum over all permutations, sum K1 and L1 from 1 to, what is it, to N. So that's the first term, and similarly for the other terms. So then we get BAB. Then the first one here is sigma of 2n minus 1. Here we have sigma of 2n. And then we have Km, Lm, Lm. So we have also to sum of all K, mu, and L mu from 1 to n. And mu is also running from 1 to 2m, and mu is running from 1 to n. Yeah. It's just everything being spelled out. Good. Now, let's reshuffle things somewhat. So these are all scalars, so we can change the order. Let me do that. And let me first collect all the B terms. Then I have B sigma 1 K1, then B sigma 2 L1, and so forth, to B sigma 2m Km times B sigma 2m L. So that's the B terms. Here I interchange the summation order. Then I have the signature of sigma here. And then the A terms are still missing, so I have A, K1, L1, all the way up to A, K, and Ln. So nothing has changed. I haven't really done anything. I've just reordered the factors and changed the summation today. That's it. But to emphasize it, let me write it like this. Because outside the brackets, the permutations do not appear. Now, what is this term that we have in the bracket? This term in the bracket pretty much already looks like a determinant, because we have these factors of the entries of the matrix, and in one of the entries we have this permutation sigma. And then there's the signature of sigma, and we sum over all permutations. So if instead of K1, L1, and so forth, we had 1, 2, and so on, then this would be precisely the determinant. All right, but we don't have that. I mean, whether the sigma stands on the first slot or the second slot doesn't matter, because the determinant of the transpose matrix is the same as the original matrix. So if you had 1, 2, and so forth, 2m minus 1, 2m here, then this would be precisely the determinant. But we don't have that. If these L's and K's are all different, then they also define a permutation, right? And then what we really have here is the determinant, not of the matrix B itself, but of the matrix B where we have permuted the columns. Where instead of the first column we have the K first column first and the L first column first, etc. And write this. So we would get here the determinant not of the matrix B, but of the matrix B with the columns somehow reshuffled. If some of the indices in here, if they agree, so for example, if K1 is equal to K5 or something like that, then we have a matrix here where two columns are equal, and then the determinant will be 0. So we can forget about those. We only have to look at those terms where in the sum over K's and L's, where they are all different, so that they define also a permutation. And in that case, we just have the matrix B with certain columns reshuffled, and this gives us the same determinant up to a sign, and the sign is exactly given by the sign of the permutations which we use to reshuffle the columns. So this will be the sign of the permutation, which is given by K1, L1, and so forth up to KL, Ln. So this term is what we have in this bracket. And then in addition we have that. And as I said, it's sufficient to sum only over those K's and L's which are pairwise different. Otherwise this would not define a permutation. But in that case, this expression gives us 0 anyway. Alright, that's good, because here we have the determinant. We can pull this in front. And then we have this factor, and then here we have all permutations, the sign of the permutation, and then the factors of A with the indices given by the permutation. This is precisely the original definition of the Pfaffian. And that's the proof. All right. So that is this invariance property. And in particular, so this is quite general because E can be anything. E doesn't have to be invertible or anything here in this formula. But as a corollary, you see that if B happens to be an orthogonal or special orthogonal matrix, so for B an orthogonal matrix, special orthogonal, then we find that the determinant is 1 here of B because it's special, and the transpose is the same thing as the inverse because of the orthogonal. So in that case we have the Pfaffian of B to the -1, which is the same thing as the transpose in that case, is equal to the Pfaffian of A times 1. For any skew-symmetric matrix. So for any A in little o of 2A. In other words, this Pfaffian is an invariant polynomial not for the general linear group, but for the special orthogonal group. Because this is the Lie algebra of this group. Right? That's the Lie algebra of this group, and this is the group itself. So we have a polynomial on the Lie algebra which does not change when we conjugate by elements of the group. It's exactly the definition of this set of invariant polynomials. And it's homogeneous of degree n. Okay, so that's what we can read off from here. So this tells us essentially already now that we can use the Pfaffian as to define characteristic classes, but only for bundles which have this structure group, not general bundles. So they must have even rank. The structure group must be orthogonal. That means the bundle must be a Riemannian vector bundle, must come with a metric, and it must be special orthogonal, so it must carry an orientation. So for oriented Riemannian vector bundles of even rank, this will give us a characteristic class. So we see this from here. Good. Yes, that's that. Another nice corollary that we can directly get from this proposition, here's the proposition from this one, is telling us that the Pfaffian is actually more fundamental than the determinant in some sense. At the moment that's not so clear because determinant is defined for all matrices, whereas the Pfaffian is only defined for skew-symmetric matrices. However, in the case of skew-symmetric matrices, it's more fundamental because, as we will see, but the following corollary tells us that determinant can always be expressed as a Pfaffian. Namely, for any matrix A, M by M matrix, we have that the determinant of A, and we now have to check the sign here. It's -1 to the n minus 1 or 2. So there's the sign of a Pfaffian. And the Pfaffian is the skew-symmetric matrix which is given by this. You just take the double size and you convert it into a skew-symmetric matrix in the obvious way. You take its Pfaffian, then up to the sign, this is the determinant. So the determinant can always be expressed as a Pfaffian, while the converse is not true. In that sense, the Pfaffian is actually more fundamental than the determinant. So you could give a linear algebra course by doing the theory of Pfaffians first, and then use this as a definition for the determinant, and then sort of derive the properties of determinants from properties of Pfaffians. You could do that. Alright, anyway, so why is this true? Proof. Well, let's do the following computation. So let's look at the following block matrices. So this is always n times 0, a, 1, a. Multiply these three block matrices, what do we get? So first we have 0 times 0, 1 times 1 gives me 1. 0 times plus 0, 0 gives me 0. 0 times something 0 gives me 0. And here I have minus identity times A transpose gives me minus A transpose. And now multiplying again, 0, 0 gives me 0. Identity times A gives me A. 0, 0 times minus A transpose times identity gives me that, and then I have 0 again. So what we get here as a result is exactly this thing that we have to insert in the Pfaffian. And if we look at the original expression, then we have some skew-symmetric matrix in the middle, and then some other matrix outside, and these matrices are transposes of each other. This transpose gives this. So we can apply the proposition where we replace A by this matrix, and for B we take that matrix. And then this will compute us the Pfaffian of this matrix, times the determinant of B. So let's do that. So from this we have that the Pfaffian of this product, which is what we want to compute, so Pfaffian 0A minus A transpose 0, is the Pfaffian of these terms. And for this we can use the formula so that we get the Pfaffian of the middle term, 0 minus identity 0, times the determinant of the thing we conjugated with, so that's this matrix. All right. Now, this matrix, the Pfaffian, we have computed over there, so that's why I did the example. So what did we get there? So we got minus 1 to the m times minus 1 m minus 1 half. So that's what we obtained for this Pfaffian. So now the determinant of this one, in order to get to the determinant of A itself, I want to have the A transpose here and the identity matrix there. And how can I achieve this? Well, I can do a lot of interchangings of columns. So I can shuffle this column all the way to the back here, and then the last column of this one all the way to the back, and the second last of the second back, etc. So this requires interchanging m columns. Right. The last one of this one is interchanged with the last one of that one, and similarly for the other ones. So this gives me a sign of minus 1 to the n times the determinant of the matrix where the identity matrix is here, 0, 0, A transpose. And now you see why I did not combine these two terms, because this one cancels directly with that one. So I have minus 1 to the n times n minus 1 half. And the determinant of this one is the determinant of the identity matrix, which is 1 times the determinant of this. And for this I can leave the transpose, so this gives me the determinant of A. And that should be the formula that we have here. Alright, nice. So if you understand Pfaffians, you also understand determinants. Good. One last point about the general theory of Pfaffians is an alternative, more geometric definition, if you wish. Namely, if we don't like to fiddle around with permutations, we can also define the Pfaffian in a different way. Namely, as follows, the position. So let A be a skew-symmetric matrix, even dimension, and now to this matrix, skew-symmetric matrix, I associate a bivector. So consider the following bivector, which is essentially whose coefficients are given by this matrix. So I take the sum over all I less than j, and then the corresponding entry in this skew-symmetric matrix times the I wedge ej, where I1 all the way up to I2n is the standard basis of R2n. So that's a bivector on R2n. Right. So we have this corresponding term, and of course this entirely this also entirely determines the matrix. We only have the coefficients with I less than j, but by skew symmetry the other ones are also determined by that. So if you know the bivector, also you know the matrix. So this is the same kind of information, having A or having I. And now the relation to the Pfaffian is as follows. Then, if we take the nth wedge product of omega, This omega is a 2 bi-vector. If we take the m's product, then we get a 2m vector. And this is then a multiple of the canonical volume vector. Which multiple is it? Well, it's the Pfaffian of A up to a factor of 1 factorial of n factorial. With this formula. So that's something we could also use as a definition if you wanted, right? So we could just say, given a matrix, consider the corresponding bivector, take it to the nth power, write it as a multiple of this. This is a 1. Then write this thing is the 1. This is an element of lambda 2m Rn R2m, so that's a one-dimensional space. So the result must be a multiple of this vector, and the coefficient appearing here is the power up to this vector of n factorial. Only m's. So, proof. And basically, let's compute the mth power of omega. So what do we get? So we have the sum y1 less than j, ai j, ei wedge ej. And now we have to take this m times and multiply. So we should maybe call this I1, J1, I1, J1, I1, J1. Similarly, M less than Jm, A Im Jm times E Im wedge Jm by Ejm. That's what we have. Right. So let's multiply this or expand this expression. Then we get a big sum. We have all these coefficients, I, J1, J1, all the way up to I, AIM, JM. Then we have E, I1, which J1, which so on, IEM, which IJM, EJM, okay. And we have to sum over I nu less than J nu, and no further restriction, except that we can remove all those terms where this gives us 0, which appears when any of the two are the same. So I will not change anything if I demand that these indices are all pairwise different. Okay. So indeed, then these i's and j's again define a permutation because they are all different. And okay, so I can then sum over all permutations S to m. Then I have as a coefficient I sigma 1, sigma 2 all the way a sigma 2n minus 1, sigma 2n. That's what I have here. And similarly, E sigma 1 all the way up to E sigma 2n. That's what I have here. And these conditions should also be noted. These conditions read as sigma 2 u minus 1 is less than sigma 2 u. That's what I have here. That's what we get. Good. Looks already pretty good. Now, for our, if you want, this is only one of the conditions of a partition. For a partition, we also have the additional condition that these pairs are ordered in such a way that sigma 1 is less than sigma 3 is less than sigma 5, etc. So the same partitions are somehow appearing various times here. Mainly the ordering of the pairs is not being done. Each pair is ordered by this condition, but the pairs themselves are not ordered. The pairs is not ordered. So if we want to convert this into a sum over partitions, then the same partition is occurring multiple times. Namely, we have to check how many times such a permutation can be reshuffled into a partition by ordering the pairs. Well, there are m pairs here, so this is m factorial times. So it's n factorial times now the sum only over partitions of the same expression. Same expression. And finally, we have to order that thing, but if we bring this in the right order, this gives us exactly the sign given by the sign of partition. So that is m factorial times the sum over all partitions. Then we have the sign of the permutation of the partition. Then these a terms. And now we bring this in the right order. And then, so now here we see that this gives us the Pfaffian, so we have m factorial times the Pfaffian of A times this volume, which is the claim. UID. Okay? Good. Now we know everything we need to know about the Pfaffian. Very good. And we can now come back to characteristic classes. Euler class. So definition. Let F be an oriented Riemannian vector bundle of rank 2n. Then, so let omega be the curvature matrix of a connection of F with respect to a local generalization. And then the Pfaffian applied to omega, and again we normalized by 2 pi as we did for Contiacian classes too. And we write this as I of F. Then this is called the Euler class. Of F. Now note, when I say I have a connection on this bundle, then I mean a connection of the bundle as an oriented Riemannian 2n bundle. What does that mean? It means that it preserves the Riemannian measure. And when I talk about a local factorization, same thing. So we compute the curvature matrix with respect to a frame which is positively oriented and orthonormal. That's what's behind this. I didn't make it say it explicitly or write it explicitly, but I'm saying it to remind you of that. And then this curvature form takes its values in the corresponding Lie algebra, which is O of 2m, little o of 2m. So it's this Q-symmetric matrix. And therefore we can insert it into the Pfaffian. Right, so if you took a connection which does not respect the Riemannian metric, or a trivialization which is not orthonormal or not possibly oriented, then this would not give you the right thing. But as long as the connection and the trivialization is adapted to the structure, we know that this thing will not depend on the choice of local trivialization, and a change of connection will replace this by something which is cohomologous to it. So that's the cohomology class of this Pfaffian, and it takes its values in. So this is a Riemannian vector bundle on the manifold n, which is a homogeneity, which is the degree of this cohomology class. It's 2m. The Pfaffian is a polynomial of degree m, but the curvature has degree 2, which is why it's 2m. Yes. Okay, good. So that's the definition of the Euler class. And why is it relevant? Because there's a famous theorem where it comes up. So let me mention this again without proof, and that's the Chern-Gauss-Bonnet theorem. And it says the following: so let M be a compact oriented Riemannian manifold, and then the tangent bundle of this manifold is then an oriented Riemannian vector bundle. So we can apply the Pfaffian to it and get the Euler class of the tangent bundle. So the Euler class of the tangent bundle of M, when integrated or paired integrated over the manifold, which has the right degree, because the tangent bundle, so maybe I should say of dimension 2n, right? Then the tangent bundle has rank 2m, and this gives us a cohomology class in degree 2m, which I can pair again on the 2m dimensional manifold to give me a number. And this number is the Euler number of the manifold. So that's chi of m, which is the Euler number. Okay. Now you could say, well, that's nice, but how about odd dimensions? In odd dimensions, we don't have an Euler class, or we have one, if you will, because then the Pfaffian is 0. And then certainly this will have a 0. But indeed, the Euler number of m is also 0 always in the odd dimensions. A compact manifold of odd dimension always has Euler number 0. You can see this. You can see this actually from Poincaré, the duality, for example. So in the alternating sum, the Betti numbers just cancel each other, because B0 and B2 and B of the dimension have opposite signs and cancel. So everything cancels in that case. So the Gauss-Bonnet theorem is also true if this has odd dimensions, but in that case it's trivial. Then it just says 0 equals 0. Alright, so that's the reason why this is important. Good, and yeah, maybe I stop here now, and next time I continue this discussion briefly, and then we will also see the answer to the question about to what extent this depends actually on the Riemann metric. If you invert the orientation, then you already see then this fundamental cycle gets inverted, gets a minus sign, and this one gets also inverted. So then the class gets replaced by its negative. That's what happens with the orientation. So it depends on the orientation, but in a very simple manner. Okay, good questions? Then I thank you for your attention.